All right, everybody, welcome to geology. Let's talk about a couple of the reading assignments, starting with what are the reading assignments? I got an email and somebody wasn't sure. So, two things. First off, it's available in the course schedule. There's all of our reading assignments and quiz dates. Make sure you see that. There's no way you're going to make it through if you don't see these quiz dates. It's going to get tough. And then these will be the reading assignments that go with it. Also, what I did is I stuck it in the top of the survival guide right there just to make sure if it's in two places, that's not going to hurt, right? So there's what we're looking for. And I'll do some quick videos just to take you through what maybe are the parts of those that I think are more relevant to what I'll put on the test anyway, right? More relevant to what we're trying to do. So in chapter 2 of the online textbook is, and I suppose I should put a link for that. I'll put a link for the online book right there as well in just a moment. The part that I'd like to focus on is starting right here with section 2.3. So before this is the Big Bang, let's just kind of say, okay, there was a Big Bang. We got this universe here somehow. And then way later, after the Big Bang, stars have formed and died and formed and died and formed and died, and that has left us with the ingredients for a solar system floating around. That's where we're going to pick up the story in this course. We're going to leave that Big Bang stuff pretty much out of it. But now that we've got the ingredients floating around in one of these clouds of gas and dust called a nebula, we can start talking about how we're going to form a planet. This textbook does one of the better jobs that I've ever seen out of any book explaining some of this. So please check this part of it out. Again, section 2.3. That gravity, at some points, when it gets dense enough, is going to take over. Gravity is dependent on the mass of something and how far apart it is from something else. So the force of gravity, there's a force of gravity between myself and this pen, because I'm a thing in this universe with mass, and this pen is a thing in the universe with mass, right? And we're this far apart from each other. So we're gravitationally attracted to each other, but it's very weak because neither one of us is very massive. What is massive enough right here next to me is the planet. That's massive enough that between my body and the planet, we pull on each other, and it's a very detectable form of gravity, right? Just if I jump, you'll clearly see I don't make it very far. So what gravity does is it starts taking these objects with mass, even if it's two tiny little particles, and it pulls them together, then they're more massive, which means there's more gravity with other particles, which pulls more towards it. Then it's more massive, which means there's more gravity, and it's going to pull more particles towards it, and then it's more massive. And you could say this over and over and over again. It's a positive feedback loop. The more massive it gets, the more it pulls in, so the more massive it is, so the more it pulls in, so the more massive it is, and so on and so on and so on. And eventually this nebula gets denser and denser and denser until we can get towards the center. A star forms. There's enough pressure to start to smash together atoms, nuclear fusion it's called, to power the star in the center, and there's all kinds of dust and debris floating around the outside. Now, where we're really concerned with this, and I won't necessarily go with other planets with anything we do, and I can't say how much I love this section of it, the accretion game, because what we've got to picture is as all of this is going around, these dusty paths, small planets, planetesimals, protoplanets are going to start to build up and collect debris and build up and get bigger and collect debris. But sometimes it doesn't quite go right. What is left almost feels, I don't know, miraculous, for lack of a better word, that some of these planets actually made it through this scenario, because you've got to be going basically all of these things. It does a great job by like phrasing it like a game. If you want to form a planet out of this chaotic mess, here's what you got to do. If you go too fast, you might take right off. If you go too slow, you might get sucked into the center. What are the conditions where you won't be crashing into other objects enough? What are the conditions where your orbit can produce one stable planet? Which happened like 8 times, right? With the 8 planets we have, plus Pluto and a bunch of dwarf planets up there, plus an asteroid belt where one didn't quite come together. Thanks to the mass of the giant planet right next to it. The asteroid belt here never quite turned into a planet because of how large Jupiter is. All right, so that out of a nebula, accretion theory kind of thing, those are things that could possibly show up, because what that's going to do is say, okay, finally, once that's all wrapped up, you got yourself an Earth, right? And that Earth is going to be the thing that we start to look at and say, when did these processes that we still observe, like all the tectonic disasters that we're going to talk about during Earth's Fury, when did those start to become a thing? So if you look at the very early Earth, what we want to find. Give me one sec. Let me find one different diagram. So with our very early Earth, what we would be looking at the beginning, undifferentiated, just pretty much uniform through it, right? Now, as continuing impacts and as some radioactivity within the Earth added heat energy, just through friction, through things banging into each other, it got warm enough where now, if it's flowing, we could have the heavier stuff, the heavier materials that are part of our planet from the beginning, from this accretion period, going down deeper and deeper into the planet and forming a core, whereas the lighter, more buoyant minerals worked their way up towards the top. And as the outside cooled, because it's up against space, we don't really have an atmosphere yet, we would start to form some kind of crust. The very early Earth, and this is not an image of early Earth because there's North America right there, right? But the early Earth would have been somewhere between these two with a very thin crust, lots of magma still happening all over the place, lots of meteorite impacts still happening all over the place, and like no atmosphere. Not a friendly place to live at all. But this would be the beginning of forming that outer crunchy layer, which still is like scary thin. If we go to like, okay, modern Earth, we're still talking about a very, very, very thin outer layer. We're going to dissect that in segment 2 when we get to tectonics. I don't want to go too deep into that. But to set the stage, we need to talk about how that Earth formed, differentiated out, cooled on the outside, and gave us different layers that we'll analyze when we get there to give us what would eventually be plate tectonics. If you've never heard that before, that's going to be the idea that that crunchy outer shell is broken into big chunks. And like half this course are the disasters associated with that. How does that lead to earthquakes in different places, very specific places, and volcanoes and tsunami, things like that. All right. So that'll be that section. So check that out up through accretion game from where I started right down through the beginning of the Earth. All right. So then we'll talk quick about time, and I'll show you one thing in the other book, and we should be ready to go for the first segment. It's been a shorter, easier one, hopefully, for everybody to get us warmed up. When we get to the second one, it'll ramp up a little bit. But that's it for now. Take care, everybody.